find a table, do all that good stuff. All right? Pause the video. All right, we're back. We are back. So, I want to type this one in. So if you've had trouble typing it in, I'll show you how to do that. So you turn your calculator on. Let's go to our y equals screen. Let's clear that out. It's a fraction again, so I need my parentheses. So it's going to be x squared minus 3x plus 2 end parenthesis divided by parenthesis x minus 2 end parenthesis. Let's hit our graph. That one looks linear. That one looks linear. Now, I want you to think about why this one looked quadratic and why this one looked linear. I want you to think about that. Take a look at those two functions and tell me why one looks quadratic and one looks linear. See if you can figure that out. These are the things the connections that you're expected to make in calculus class. Okay? Looking at a graph, looking at a function, looking at the equation and trying to make some conclusions. Well, if I were to take something that was x cubed and divide by x, what would I get? I would get something that's x squared, which is why that one looks quadratic. If I had something that was x squared and I divided by x, I'd be left with something x, which is why that one's linear. Okay? So, back to the problem here. Back to the problem. So, what do I want to do? I want to set up a table. We'll do that first. Second table set. Now this time I'm approaching 2, so I'm going to make this 1.97. And I can still use my 0.01. And then I hit second table, and my table comes up. How about that? So we're looking at the table there. Okay, we're looking at the table. Let's set that up here. Okay, here's my x, here's my y. 1.97, 1.97, 1.98, 1.99, 2, 2.01, 2.02, and 2.03, 0.97, 0.98, 0.97, 0.98, 0.99, error, 1.01, 1.02, 1.03. Kind of weird how that happened, isn't it? I mean, those numbers line up. They certainly didn't intend for that to happen. So looking numerically, what do we think our y values are approaching? What number are they approaching? As I come from this side, they're approaching 1. As I come from this side, they're approaching 1. So I would say it's equal to 1. Now, if they ask you to do it graphically, using a graph, well, the graph would look, we saw what the graph looked like, right? It looks something like this. And then we know there's going to be a hole there, okay? So, with graph, when you're doing it graphically, it's good to include a couple points. Remember when I did those, I hit the second trace value, okay? So, I could do that, all right? You could certainly plug that in, and you could plug in some values to back that up. So let's do that. So let's plug in a few values to back that up. Let's do 1 point, what do we get close to 2? Okay, I can use 1.999. Okay, so I hit second calc, value 1.999, and it gives me 0.999. And I could do another one and do second calc value 1.99999. 1.99999, and I get 0.99999. 0.99999. And then I'll do one from the other side. 2.0001. So second calc value 2.0001, and I get 1.0001. And you can see here as well that my values are approaching 1. Okay? So we did that graphically, we did that numerically. Again, they're probably only going to ask you to do it one way, okay? They're probably going to only ask you to do it one way. So, while we're looking at this, okay, while we're doing this stuff, I do want to put on, I want to kind of give you an introduction to next section while we're doing these, okay? And how to do them analytically. Analytically means using algebra, okay? So analytically means using algebra. We know that we found that the answer was 1, so I'm just going to put that 1 over here so we remember what we found, okay? So using algebra, in this case, what I can do is I can factor my numerator. I can factor this to x minus 2 and x minus 1, and then my x minus 2's would cancel. So I'm left with the limit as x approaches 2 of x minus 1. Well, I have no more problems plugging into 2. The problems have been eliminated because I was able to cancel with my fractions. So when I put in 2 minus 1, 2 minus 1 is 1. Again, I found the answer. That's the third way that we're going to do these, okay? That's the third way. So back to that first one that we did. The limit as x approaches 1 of x cubed minus 1 over x minus 1. If, you know, in section 1.3, they want us to do this. They want us to do this by analytically. We could factor that top. The limit as x approaches 1, that factors to x minus 1 times x squared plus x plus 1 over x minus 1. Now those would cancel. Take a 1 and plug it in. 1 squared is 1, plus 1 plus 1. I get 3. That's the same thing we got, doing it graphically and doing it numerically. Okay, so just a little preview for section 1.3. Or sometimes it's a way to check your answer. All right. So, a couple things left to look at. I think we're just going to put this up here. I don't know if you'll be able to read that. I guess I'll write it. All right, here we go. So the informal description. This is right out of your book. The informal description, if f of x becomes arbitrarily large, arbitrarily close, sorry, to a single number, they're going to call that L for now, as x approaches C from either side. The limit of f of x as x approaches C is L. Okay? So what does that mean? The limit as x approaches C of f of x is equal to L. That is your informal description. Okay? I strongly suggest that when I give you the notes that you take those down. There will be times that these are answers to test questions. And if you don't take good notes, you're just not going to have that. Okay? You will not have that. So, this is the informal description. Okay? Now, there is a formal description. Okay? Formal description. On page 51, but we're not going to cover that, okay? That's usually only designed for people who major in math in college. Quote, formal description. This is what we're going to use, the informal description, okay? So, we've got a few things left. Let's take a look. And then we'll be done with 1, 2. you think it's long taking notes, it's long presenting this stuff too. So now we're going to talk about limits that fail to exist, at least for now. Limits that fail to exist. Okay? I had f of x equals 1 over x. So here, the limit as x approaches 2, guess what? No problem. No problems here. Nothing to see. Okay? The problems come in when I have it approach a different number. Okay? So this is an example of a limit that doesn't exist. Let's say I had this. The limit as x approaches 0 of 1 over x. Okay? So if I were to do this and type this into my calculator, okay? So I have my y equals, I clear that out. This is going to be 1 divided by x, okay? And then I'm going to hit second table set. 0 is the number in question, so I'm going to make this, I don't know, what do I want to put for 0? Negative 0.9? No, not. Negative point, let's do negative 0.01. Okay? So, actually, do I want, yeah, I could do either positive or negative there. So let's go to our table and see what that looks like. Take a look at our table here. If you look at our table, okay, you might not be able to see it, but when I plug in negative 0.01, I get negative 100. When I plug in 0.01, I get positive 100. Okay, so this one doesn't exist. In order for a limit to exist, they have to approach the same y value as we come from both sides. Okay, so this is a limit that fails to exist. Okay, does not exist. Let's look at another example of a limit that doesn't exist, and then I'll put up some notes for it, okay? So let's say I had this. F of x equals the absolute value of x minus 1 over x minus 1. Okay, and I'm thinking of that as the limit as what value of x is going to be a problem here? Take a look at your function. What value of x is going to be a problem? Well, 1 to be a problem, right? X minus 1 over x minus 1, top being absolute value. So I've got to figure out how to type that in, okay? So let's look. I think it's with catalog, okay? So we're going to probably have to fiddle with this a little bit. I don't spend a lot of time graphing absolute value functions on it. So let's go to our y equals, let's clear that out. And then let's use catalog, which is down here, okay, with 0. So I hit blue 0 for catalog. And I want absolute value. So if I hit absolute value, then it has that, okay, which is what I want. X minus 1, I gotta get out of that absolute value. And then divided by, I don't know if I should have made parentheses around that. I don't know, we'll see. I'm not used to the order of operations in this calculator. It's different than the one that I have. Okay? And now let's hit graph. Well, let's look what's happening there with that graph, okay? As I'm coming from the right side, the positive side, my y values are approaching 1. As I'm coming from the left side, they're approaching negative 1. Okay, so there's a break in the graph. Okay, there's a break in the graph here. But because the limit here is 1 and the limit here is negative 1, that limit doesn't exist. Okay? So here are your rules for that stuff. Here are your rules. Limits that fail to exist, you can keep it underneath here. Okay, a little more formal right now. Number 1, behavior that differs from right to left. Okay, so the limit as x approaches 0, we just had it, x minus 1 over x. the absolute value function. On one side it was approaching one number, on the other side it was approaching the other number. Behavior differs as you go from left to right. That's one example that doesn't exist. Number two, something that's called unbounded behavior. Okay, unbounded behavior. So that means we approach either infinity or negative infinity. Okay, and that was the first one that we did. I don't know if we ever looked at the graph, but that was this one here. Okay, so when you have graphs that do one of two things, they do this, or sometimes they do this, here, and then here they do this. Okay, this is another example of a limit that doesn't exist. And then the third type, okay, the third type is what's called oscillating. O-S-C-I-L-L-A-T-I-N-G, behavior. So let me just get a book. It'll take me a minute here. Right from the closet. So oscillating behavior is stuff that does this. Okay, that's what your graph does. It goes up and down, 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 in such a small space. Okay, that is called oscillating behavior. So I'm going to show you a picture of that. There's a picture in the book. Right here. Okay, here's an example of oscillating behavior. The graph starts off like this, and then it goes up and down so many times that you can't tell where it's going up and where it's going down there. Okay, that is oscillating behavior. So you might want to draw that picture there to get a better look at it. Okay, so that, ladies and gentlemen, is a good start to section 1.2. I do have other problems that we'll practice. We will probably do those in class. Hopefully that makes sense. If it doesn't, send me an email.